question or what do you call this, or anything clarity that you'd want or something, please just unmute your mic, because I really can't go back to Teams now to access to see the questions that you guys might have asked. So if you have any question, I feel like you can just unmute, then you ask. So let me look for the notes where they. Okay. No, okay, it's actually continuation. Why didn't you use? Okay, sure. Okay, so now today we are gonna do, just take a look at the document that I sent now. Like the first, what do you call this? The first question that I posted there, I just counted it as a recap of counting methods. So it's gonna be counting methods with a twist of what? Probability. You see? So just to clarify one of two things that you guys might not be aware of, I'm really not sure if you guys were taught or something, I really don't know. But when it comes to counting methods and probability, isn't it? Firstly, I think as you can see the questions, isn't it all this time you were used to being asked in how many ways can you group this, that, in how many ways can they be consecutive, what, etc., etc. But now in this scenario, or these scenarios that we have right now, there's a twist now to the question, because it's now asking you for the probability unto which a certain scenario can be modeled or something. The computation is just the same, more or less. So let me look for my calculator. The computation is actually one and the same thing, it doesn't change. All the counting methods knowledge that you had or that you acquired up until now, all the methods that you actually use to apprehend such counting methods questions, it doesn't change. But the only thing now that changes is you are now working with what? You're now working with probability. Sorry. We are now working with probabilities. And when you're working with probabilities now, we are not being asked of the number of ways or something, but you're asked of the what? Of the probability. But it's actually one and the same thing, because what you do is, let's assume you're given a question, you're given, we'll just look at the question that the first question in the document I sent now. Let's assume you are given maybe a counting method scenario that you are used to, isn't it? One, it can either be the sharing method, isn't it? Then two, it can either be the grouping or something that you already know, those questions where they say that the 12 cars are not supposed to be serviced consecutively, blah 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 blah, all that stuff, isn't it? You just compute the number of ways in a way that you already know, isn't it? Let's assume we have what do you call this? Let me look for the word, what do you call this? Let me just write success, isn't it? So let's assume you have the word success now. And with the word success now, we are asked in how many ways. I'm just gonna tackle it in the first instance that you are used to. They can ask you how many different ways, how many different words can you come up with from what? From the word success, isn't it? From the word success that you already have here. So isn't it, you already know that the conventional method of doing it is, we'll say it's gonna be 9 factorial divided by 4, we just have to account for any repetitions, isn't it? So it's 2 factorial for C times 2 factorial for what? For S, isn't it? Then when you calculate this, the answer that you get is 2 factorial times 2 factorial. It's just going to be what?
It's supposed
9.
to be 3 factorial for S.
Oh, sorry. Thank you. Thank you so much. 3 factorial for S. So the answer that you get here will be, in this case, it's going to be 30,240, isn't it? But in this thing in now that you are doing, like the probability, they'll ask you, like, what is the probability? What is the probability that you can formulate a, how many words? 1, 2, 3, 4, 5, 6. Wait, why did I say 9 here? Oh, I'm sorry. It's not supposed to be 9. Like, how many words are these? It's 1, 2, 3, 4, 5,
7.
6, 7. Not 9. 7. Thank you. It's not supposed to be 9, but it's supposed to be 7. Yeah. So it's supposed to be 7. Yeah. So if you say 7 factorial divided by that, your answer will be 7 factorial, which will be 420, isn't it? So if it's 420 now, then the question now that addresses what you guys are actually doing now is, what is the probability that you can formulate a 7-letter word from what? Success that you already have, isn't it? So what we know is, let's assume that they did not ask us of the probability, isn't it? Like they had not asked us of the probability. So if they had not asked us of the probability, how would you compute this question? You'd compute it as what we did here. But now that they're asking you of the probability, how would you calculate the probability? The probability, obviously, it's gonna be the number of, what do you call this? The number of combinations that you can come up with, isn't it? Divided by the sample space. Keep this in mind. Whatever it is that you are used to now, it's just going to apply for the numerator, isn't it? But now for the denominator now, it has to be the sample space that you have to figure out on your own. But in most cases, it's actually easy. Because for this question now that I wanted as question 2, they're asking of the probability of formulating a 7-letter word. So we said the probability is equal to the number of combinations, isn't it? How do you calculate the number of combinations? It's what we've been doing since, which is this part, isn't it? Which is just 7 factorial over 2 factorial times 3 factorial, which gives you what? 420. That's how you calculate the sample space. But you divide, so that's how you calculate the number of combinations. But you divide this by the sample space, isn't it? Like, what is your sample space in this case? Your sample space is just 1, 2, 3, 4, 5, 6, 7, 8 factorial. Like, which, oh, is it 8 or 7? 1, 2, 3, 4, 5, 7, sorry. It's gonna be how many? 7 factorial divided by whatever repetitions that you have in this case, which is just 2 factorial times 3 factorial. Then you get 420 also. So in this case, your answer is 1, isn't it? Like your answer would be 1 because like it's just a question that I just formulated now for you to actually see how exactly you go about such questions or problems, if I should call them that. So you divide whatever combination that you were used to or whatever computation that you've been doing since you started doing counting methods, you divide it by the sample space only. The moment you divide the sample space,
So,
then you get your probability. Then that's it. Yes.
so just to clarify, with the sample space, if you have no repeating letters, then if your word has 12 letters, then your sample space is simply going to be 12 factorial. And then
It's
if you have
simply,
repeat
sorry.
letters, then you divide with the number of repeating letters.
Then you divide the number of repeating letters.
So that's always the case with the sample space part.
Yes, most of the times when you're dealing with such questions, which have words, because this question that we did now is the one that has words, isn't it? Then we will do the cars problem that we actually did yesterday, but we are just gonna incorporate probability in it. Then I'll also tell you how you go about the sharing one with probability also. Then I feel like that will be
Okay.
it.
Okay, thank you.
Sure. Okay. So this is how you go about it. So when it comes to probability, here's what you're supposed to know. So case one, your probability is always supposed to be in the ranges of let's say probability of A. It's always supposed to be in the ranges of 0 to 1. Whenever you get a probability that is greater than 1, which is something that's actually common when you're doing counting methods, at least like that's how I used to go about it when I did stats. Like you compute whatsoever it is that you do, isn't it? Then you see that your probability is maybe like you see in this case, isn't it? Like we just said like the sample space, so the probability is gonna be the number of combinations over what sample space. Like I don't know, you make a mistake somewhere and then you say your maybe number of combinations is gonna be 420. Then I don't know, you make an error when you're doing your sample space, then your sample space is 3 factorial. Then the moment you compute this to calculate your probability, you get an answer that is greater than 1. You see, so it's gonna be 420 maybe divided by 6. Then I don't know whatsoever answer that you get. Let's say it's like 80. I'm just assuming, I'm not saying it's correct. But if you get an answer that is 80, please know that you would have done something wrong. Definitely. Because probability is supposed to be between 0 and 1. And you see it more often when you're doing these probabilities because you get these answers first time, but you know that you might have made a mistake somewhere. And one thing that I've also seen is the mistake that you'd have made whenever you get such an answer is the sample space. I feel like for the numerator, considering everything that we've been doing in counting method, everyone can actually come up with a figure for the numerator because that's what we've been doing so far. But now when it comes to what do you call this? When it comes to the denominator, which is the sample space, we normally make mistakes. Or let me say I normally made mistakes. I don't want to speak for everyone, but yeah, that's a common mistake that I usually encountered. So please take note, it's supposed to be between 0 and 1. And even if you get an answer, like let's assume, because in one of the questions that I was doing now, I saw that you can actually come up with an answer that is like maybe it's gonna be 1.23 times 10 to the power negative 9. It's actually acceptable now because such an answer will actually exist. So just write it as it is. Then when you're trying to compute it on the what do you call this? On ULWAS or something, you write it as 1.23 e negative 9. So this e, which is the exponent, is actually a representative of 10 to the power whatsoever it is number that you write here. Keep that in mind. But please, there's no answer that is less than 0. I'll always emphasize this. There's no answer that is less than 0 or greater than 1. Such an answer does not exist, isn't it? I feel like it's fine. Then let's do this one question for cars, which is the one that I call the recap counting methods plus probability. It's actually the same question that we did yesterday. Like it's saying we have 12 different cars. Then of the 12 different cars, we have 4 BMW. Then we have 4 Toyota. And we have 4 VW that are booked, serviced, one after the other. That's fine. Then A is saying, what is the probability that cars made by the same manufacturer, saying cars made by the same manufacturer are serviced consecutively, isn't it? So for this one, I'm not gonna do like solution, isn't it? I'm just gonna come here because we did it yesterday, if I'm not mistaken. I'm a bit lazy to do it though, but let's see. Okay, I think it's this one. Is it? No, it's supposed to be somewhere here. Because a service code, yes. This is the question that we did. So isn't it, as I was explaining here, like you can either take this case where BMWs are serviced first, then like BMWs, sorry, are serviced consecutively only, then VWs only or Toyota only, then you compute you compute as we did here. Or we can consider that when all the VWs, like whenever the manufacturer starts servicing VWs, is only gonna stop until all the VWs have been serviced, isn't it? Then it goes on to BMW, then it goes on to Toyota also. Then we computed it like this, isn't it? So our answer was 82,944. I'm just gonna take it just now. So we said that our answer, so we said probability, isn't it? It's gonna be the number of combinations, or yeah, I'm not sure if the terminology is fine, like number of combinations over the sample space, isn't it? So we already know that the number of combinations that we can have for this, we said it's sorry, let me look for it. We said it's 82,944. It's gonna be 82,944. That's your answer for the number of combinations, isn't it? Then it's gonna be divided by what? By the sample space. Like what's our sample space in this case? Obviously, our sample space is just gonna be what? 12 factorial, because they are saying what do you call this? Like they are asking, like what's the, like you already know that your cars are different, isn't it? So if your cars are different, then your sample space is definitely gonna be what? 12 factorial. Coming back to the question that someone just asked now, like if you are dealing with different objects, obviously it's just gonna be 12 factorial, isn't it? But let's assume he had said that the BMWs are identical, the Toyotas are identical, then the VWs are also identical. If that was the case, then your sample space was gonna be 12 factorial divided by 4 factorial for the identical VWs, 4 factorial for the identical BMs, then 4 factorial for the identical Toyotas. This will be your sample space. So you divide this answer 82,944 divided by your sample space. In this case, it's just 12 factorial, because we know that our, what do you call this? We know that our all objects are different. So if they are different, then you just divide by 12 factorial. Then that's it. So if you want to do this, your answer will be 0.000017316 blah blah, which is 0.0002 approximately, which is the answer that's given in this document.
Can I ask, with regards to decimal places, are we going to be told how many decimal places we're supposed to round off to? Because like,
yeah, you will be, but please, one thing that I've seen with them is try to write as much as 4 decimal places.
okay.
But I'm sure your exam, what do you call this? Like your test thingy will tell you the number of decimal places that you are supposed to round off to.
So I guess
Plus,
also it might be safe to write
sorry?
both like you did, so that, like I'm
Yeah,
saying, it
you can.
might be to write both of them like you did, so that he can see
Yeah.
what you rounded off.
Yes, yes. Plus, the good thing about this test is it's not automated. Like by automated, I mean, okay. Like I'm saying, it's not automated in the sense that, oh, sorry. It's not automated in the sense that, because you, like you see with him, is some of his answers are wrong or somehow, like as he always said, because he actually approached us. Then he was like, no, he's gonna fix everything. That's what he told me. Like it's gonna fix everything. We try to go through all the quizzes that you guys have done up until now. Then we rectify the answers. Then the moment you rectify the answers, it's just gonna remark everything. Then you'll be allocated your marks accordingly. Like if your answer was right in the first place, and it's actually coinciding with what we would have gotten, then you get your marks. But now the good thing about writing, like physically, is obviously you get part marks first and foremost.
Can I
Yes.
please interrupt? I'm sorry. Like the time, we are running out of time. So I sent you a similar question to the ones who are getting on the quiz. Can you please
Okay.
help us with that one?
Okay, it's actually fine. It's like we'll do this because I just wanted us to do this probability one, then go on to that one, because this is literally base theory, and some of these questions that you have in your quizzes, I just confirmed now they are actually in this document that I sent to you now. You see.
Okay.
Yeah. So we'll just go through one or two, then you will be able to do everything. Like I feel like we can be done by 10 o'clock. Because I can see that your quiz is closing at 11. So by 10, we'll be done. Don't worry. Yeah, because I actually have this question in this document. You see it. That's what you actually started with. So don't worry at all. So yes, this is how you go about this. So for part B is saying no two vehicles are serviced consecutively, isn't it? What you do is you obviously do what we did here yesterday when you're doing this, like what you've been doing for counting methods, which is this: no BMWs are serviced consecutively. So you group your sample spaces as this. Sorry, you group your positions as this. Then you calculate also if it is that you calculate here. Then you divide your answer by 12 factorial, which is the sample space. That's it. Then you go on to C, which is actually the same thing. The first cars, the first and the last are BMWs and whatsoever. That's fine. You can do it also. You compute it just as how we have been doing all counting methods questions. Then after doing so, you just divide by your sample space, which is 12 factorial in this case. Then that's generally it. That's how you go about probability coupled with that, which with with counting methods. So now if it's a
Can I
sharing
please ask
problem,
a question?
yes.
On what you said, like I want to know, when you say we do it like the way we used to, would I include all the possibilities or maybe just that portion that they want? Like maybe it should be the first three. Am I gonna take the first three and all the possibilities over the sample space, or just those first three?
Over the sample space. Like okay, like what exactly do you mean by first three?
Like for instance, if they say that I should arrange cars, maybe BMWs, that they are the first three, right? So
Okay.
for the probability of finding, I'm just
Oh,
making I'm just making up
okay.
something.
Okay, so what you do is you do it the way that you've been doing it since. Like you are told that the first three are supposed to be BMWs, isn't it? You just group them in the way that we have been doing. So like this is 12, then you know that these three is supposed to be BMWs. Then how many of the BMs do we have? We have four. How many are we choosing? Three. In how many ways can you group them? In three factorial ways. Then times whatsoever it is that is here. Like in this case, it's gonna be is 3, 9. So it's going to be times. These times, we said there were 4, 8, 12. 12 minus 3, that's 9. Here it's going to be what? Times 9 factorial. This is how we've been doing it, isn't it? Like, it doesn't change. But the sample space now is going to be all the cars that you are arranging in any way. Like, you have 12 cars. So in how many ways can you arrange these cars? It's just in 12 factorial ways, regardless of the conditions that you are given. Because I feel like the sample space disregards all the conditions that can be applied, like phase two whatsoever. Like we really don't care about that when we're dealing with the sample space. Sample space is just 12 factorial. That's it.
Okay, I get you. Thanks.
Okay. So when it's sharing now, sharing probability of sharing whatsoever, probability. It's actually the same thing, isn't it? Yesterday we were saying, like you have two cases. The first case we said when they're identical, then second case when they're what? When they're different. So when they're identical and when they're different, how do you go about it? You just do whatever it is that we've been doing now. Like let's assume it says Nehemiah gets at most 16 or something, or etc. etc. So let's assume for this, like I'm just formulating it. Like let's assume he's saying Nehemiah, isn't it? He has maybe 12 different or similar or identical, actually. Identical what? Pamphlets. Now let me start with the one for identical pamphlets, isn't it? That is sharing maybe amongst A, B, C, and D, isn't it? Then he says in such a way that Nehemiah gets maybe at most 10 pamphlets. So if he gets at most 10 pamphlets, isn't it what we did yesterday? Like we said, if he gets at least at most, excuse me, if he gets at most 10 pamphlets, what you mean is we'll say the same, like the whole, like it's gonna be n plus k minus 1 choose n, isn't it? Which is the whole sample space in this case, isn't it? Minus for when Nehemiah gets, isn't it? In this case, I said he gets at most 10. So in this case, we subtract for when Nehemiah gets 1, then minus for when Nehemiah gets what? For when Nehemiah gets 11, then for when he gets what? 12, isn't it? Like this is the conventional way that we've been doing it since. Then you get your answer, which is fine, isn't it? But now that you are dealing with probability, you divide by the sample space. So in this case, when you're dealing with sharing, isn't it? What is your sample space? Your sample space is always going to be n plus k minus 1, choose n. It doesn't change. So you do whatsoever computation that you make here. Sorry. You do any computation of your choice here. Then you divide by the sample space, which is literally this, that you subtracted your entities from. This would be your sample space. So when you're dealing with sharing of identical objects, you compute the same way that we've been doing since. Then you divide by the sample space. The sample space is always, and I'll repeat, always going to be n plus k minus 1. Choose n. So let's assume for the questions that we did, the sharing questions that we did, if it's n plus k minus, like, sorry, for all the questions that we did yesterday, like let's assume they were phrased like, what is the probability that Nehemiah gets it most, what. You compute it like this, which is perfect. Actually, let me look for it though, just to make it clearer. Okay, like this one. Because isn't it, it was saying we have 12 balls leveled 1 to 6. Then in how many different ways can all 6 get at most 9, isn't it? So let's assume the question is in how many, like what is the probability that all 6 gets at most 9? Then you do this calculation here, this computation here, like everything that we did yesterday. You do this here. Then the moment you get here, you get your answer, isn't it? The answer, like whatever answer that you're gonna get here, then you divide it by the sample space. The sample space, as we said, is always n plus k minus 1. Choose n. So in this case, your sample space is 17. Choose 12, which is the one that you said, what? Which is the one that you calculated here. So you do your computation as usual, then you divide by n plus k minus 1. Choose n, which is your sample space. That's it for what? For sharing of identical. Then if it's different, isn't it? Yesterday we said when you're dealing with different things or something, like you use this, isn't it? Like the table thing. So from this table, like the question is saying you have 9 panelists that can vote for, against, or abstinence, I think. Then in how many ways like I don't remember how exactly the question was, but either way, let's assume the question was, what is the probability that, isn't it, like the probability of I don't know whatsoever it is that's happening. So In this case, you do this computation as we did here. Like it won't change. It's actually doing the same thing, but you divide by the sample space. The sample space in this case now is like, what do you call this? In this case now, it's gonna be 3 to the power 9, I think. Yeah, it's gonna be 3 to the power 9. Because this is saying we have 9 panelists. Oh, actually, we have 9 panelists that can vote for, yes, that can vote for, against, or abstaining from that. So in this case now, this will be your sample space, 3 to the power 9 when you have tables. Then this one was a trial run, if I remember very well. Then yes, when you're doing a sharing of identical, this is how you do it. Now, when you're doing the sharing of different objects, as we are saying, let's assume you have A, B, C. Now we have 2, 3, 3, 3, 1, 3, 3, 6, 7, 8, 3, 6, 7, 8. Just want to maintain 8. So it's going to be 4, 5, 6, 7, 8. Like, let's assume these are the possible combinations that you get. And they are telling you that you have maybe 8 things. I mean, that's why I was maintaining a total of 8 here. So in this case, it's going to be what? 8 factorial divided by 1, 2, 3. 3 factorial times 3 factorial times 2 factorial. Then you also do the same for this one. Then you also do the same for this one. Then your sample space now, it's going to depend. Like, it depends on how the question is structured. Because your sample space can be 8 factorial, or it can be 3 to the power 8. So you have to see whether or not it's implying the multiplication principle, which is this, or it's just a choosing thingy, which is 8 factorial. This is something that we have been doing, but I just wanted to clarify on this part. Do you have any questions pertaining to this before we move on to base theory?
Can you please repeat? You mentioned it can either be 8 factorial or 3 to the power of
Oh,
8. And how do
okay.
we
So
choose which sample space to use?
I don't know, because if only I had a question, isn't it? Because actually, let me try to think. There's this one that you did in class, if I'm not mistaken. Like, you had, I think. Let me see. I'm trying to recall that question, but I'm not sure if we actually did it yesterday. Yeah, like we didn't do it yesterday. Like, maybe you have, like, let's assume for this one, isn't it? You are sharing these 8 different, do this. Like, you are sharing these 8 different objects amongst how many recipients? You're sharing these 8 amongst 3 recipients, isn't it? So you're sharing these 3 amongst 8. We say that, like, let's assume you do your things, then you come up with these combinations in your table. Then you calculate them as 8 factorial divided by these values factorials. Then you add, then that's fine, isn't it? So what you do is, actually, I feel like it's like, I would like to call it maybe a litmus test or something, though it's more or less like gambling, but it works. Like, it worked for me, let me put it that way. So if you're not sure of which one now you're supposed to use, like, let's assume in this case, isn't it, I said it's 8 factorial or 3 to the power 8, isn't it? Like, it's either 8 factorial or 3 to the power 8. Like, you're not sure of which one exactly you're supposed to use, because you can use either one of these two, if whether or not you know that it's a multiplication principle. This is the multiplication principle, and this is the one for combinations that you have been doing. Like, it will depend on the question. Like, you see which one to use and which one to not. So the litmus test goes like this. What you do is you calculate as we calculated here. Then you get your, isn't it, to set probability. It's going to be the number of combinations or whatsoever divided by the what? By the sample space. So you're already done with the numerator. Then you come on to the sample space. What the sample space normally does, like how it guided me was, let's assume for this one you get, like, let's assume the numerator is 420, isn't it? Let me just stick to 420. Then you have these two choices that you want to choose from, 3 to the power 8 and 8 factorial. Like you want to choose either one of these two as your denominator. So you actually use both of them. You see, then maybe this one is going to be 3 to the power 8, then the other one is going to be maybe like 8 factorial. So when you compute these, normally what I saw is there's definitely one answer that's definitely wrong, isn't it? And that wrong answer will give you a value that is greater than 1. Like this is where you get thousands of probability, what. So the moment you do that, you know very well that your answer is wrong. So you have to go on now to the second one, which is maybe in this case might be 8 factorial. And like I'm not sure which one is it, because yes, there are times though that the answers might not be greater than 1, but it's rare. You see, so you have to use either one of these two, and you see, because definitely one of them, most of the times when I was doing this, most of the times one of them is definitely greater than 1, which is actually wrong. That's when you know that no, whatsoever it is, a denominator that you used in this case is wrong. So you have to change. Does it make sense?
So just to confirm, the 3 to the power of 8, is it 3 because of like it falls under 3 categories, and then 8 is the number of rows?
8 is the number of in this case, let's assume he's sharing 8 cans.
Oh, okay.
Yeah. It's just eight objects that are being shared. So that's where you get the 3 to the 8. Is it clear now? Hello?
Yes.
To the person oh, okay, sharp. Now, let's go on to what do you call this? Let's go on to what was my thing? Let's go on to base theory. I'll try to be as quick as possible. I want to give it time to write, because I can see from my sign that it's saying this thing is going to be due at 11. I think, is it today? I think so. So, base theory. It's base theory. So, guys, this is what you're supposed to know, because I'm not gonna go through all the theory for base theory because I don't have the notes right now, and I'm just gonna say everything that I know about base theory, and it's actually gonna be directed to most questions that you do, and it will make sense the moment you do one or two. So, for probability, isn't it? As I had said earlier on, like yesterday, there are cases that you have to deal with. Like let's assume it's probability of A union B. This is modeled as probability of A plus probability of B minus probability of A intersection B. You'll be given maybe some instances that you have to apply this formula. Like this is more or less of a universal probability formula with regards to set theory. Keep this in mind. Then you also have something that they call conditional probability. So what's conditional probability? Let's assume it's probability that A, probability of A occurring given B, isn't it? This is going to be the same as probability of A intersection B divided by probability of B. This is how you compute what? Conditional probability, isn't it? Then also, one thing you have to know is probability of A given B is not the same as probability of A of, sorry, probability of A given B is not the same as the probability of B given A. These are two different things, isn't it? Because isn't it we said probability of A given B is equal to probability of A intersection B over probability of B. Then probability of B given A, it's going to be probability of B intersection A over probability of A. So you can see the difference, like where the difference in these formulas arise. It's simply because of the denominator. The numerator is the same. Probability of A intersection B is actually the same as probability of B intersection A. Then this is from the, what do you think it's commutative? I forgot. It should be the commutative principle. I'm not sure if it's commutative or whatsoever. I don't remember the last time I did groups, but yeah. So please keep note of what you just did here. So, and also the probability of A given B times probability of B is going to be probability of A intersection B. I just made, like from this formula, I just made probability of A intersection B the subject of the formula. So it's just probability of A given B times probability of B. That's it. Keep this in mind, isn't it? Does anyone have any question pertaining to what I just said now? Because I feel like the best way that you can explain base theory is if you actually do a question. Okay, so I assume everyone is okay with it. Then please look at the document that I sent. We're doing question 1. Because I'm sure if you can do question 1, 2, and maybe 3, then you guys will be okay to actually attempt the quiz. Because question 2 is similar to the question that someone just told me that they sent me now. Like I can see it on my device now. But yeah. So question 1 is saying incoming calls to a customer call center comes from 2 districts. One thing that you have to do now, ladies and gentlemen, is whenever you're dealing with such probabilities, write everything down. Like draft everything that you have down, isn't it? So you know that it's coming from what? 2 districts, isn't it? Because I feel like if you can follow the procedure that I'm gonna try to explain to you now, everything will actually make sense at the end. So you have 2 districts, isn't it? Then you have district A, which receives 60% of the calls, and district B, isn't it? So they are saying district A is 60%, isn't it? Then district B is going to be 40%. Then also, please, isn't it we already said that the sum of all probabilities is supposed to add up to 1? In this case, he told you that district B is going to account for 40%. But in other cases, he might not tell you, because he will just tell you that incoming calls to a customer call center come from 2 districts. District A, which accounts for 60%, then district B. For district B, it doesn't tell you the percentage, but you have to know, because like you already know that no, all probabilities account to 1, which is just 100%. So in this case, even without being told the percentage of calls coming from B, you already know that it's 40, like 100% minus 40. Then you get what? 40%. Please keep that in mind. So in this case now, knowing very well that you are dealing with probabilities, you can actually write these as decimals. Like there's no reason to write the percentages. So just 0.6, then this case is 0.4. This is the first information that you have. Then they tell you that of all the calls coming from A, isn't it? So now they are saying of all the calls coming from A, let me write P here. Sorry, just realized now. For it to actually make sense. Okay, so in this case, it's going to be probability of A, it's going to be 0.6. Then probability of B, it's going to be 0.4, isn't it? So you have probability of A, you have probability of B. Then they tell you that of all the calls that are coming from district A, like the moment you hear this, just know that this is a condition, like it's literally a condition, because they are telling that, okay, of all the calls that are coming from A, which means that A is the condition that you have, isn't it? So it's going to be the probability of something, I don't know what that thing is, given it's coming from A. That's what conditional probability means. Because if it's conditional, like if it say probability of, like in this case, it's probability of A given B. So in this case, they are saying of all the calls coming from district A, you already know that your condition is going to be what? A, isn't it? Then we want to know whatsoever it is that they're talking about. Then they said 56% are dissatisfied. Like let's denote dissatisfied. What's going on? Dissatisfied as what? As D, isn't it? So it's gonna be probability of D given A. It's gonna be what? 56%, which is 0.56. That's one thing you have to know, isn't it? So probability of dissatisfied, given that they are coming from what? From A. Please don't make the mistake of interchanging these two. Because if you say probability of A given D, it's actually something different from probability of D given A. So you have to understand the question thoroughly for you to actually know that which of the condition, like which of the things that you are given is a what? Is a condition, isn't it? So in this case, we know that the condition that we have is it's coming from A, isn't it? So its probability of dissatisfied given is coming from A, gonna be 56%, which is 0.56. Are dissatisfied with the service offered by the call center, while 33% are moderately satisfied. So, okay, so let me remove this. We'll write it at the end. So probability of dissatisfied is 0.56. Then probability of moderately satisfied, let's denote it by M. Moderately satisfied, given they're coming from A, it's gonna be 0.33. Then probability, and the remaining 11% are very satisfied. So probability of very satisfied, given they're coming from A, is definitely going to be equal to what? 0.11. Also note, if you add these two probabilities, it means that, like, if you add these three probabilities, the sum will be what? Will be 1. Keep that in mind. Like, it's supposed to be 1 always, actually. Okay, so you have this, isn't it? We are done with what? District A. Then we go on to district B, which is probability of B. Initially, we said it's what? 0.4%. 0.4, I mean. Then of all the calls coming from B, so now we already know that our condition is what? Is B now. See? So our condition is what? Is B. So the probability that they are dissatisfied, probability of D given B, it's gonna be 0.46. Then the probability of moderately being satisfied of M given B is gonna be 34, which is 0.34. 0.34. Then the probability of being very satisfied, given that they're coming from B, is gonna be 0.2. You see? Note, if you add this, they'll give you 1. Okay, now we are done. Then what is the probability that an incoming call to the customer service center will be a form, I don't know, will be a form of customer who will be dissatisfied with the given by the courses whatsoever. So what they are saying is they are looking for the probability that the customer is what? Is dissatisfied. You see, like we are calculating the probability of D. That's what we want, isn't it? Like we are actually calculating the probability of what? Of D. But in this case now, what does this imply? Like we have two cases onto which the dissatisfaction can come from. The two cases are, it can either be like the customer is dissatisfied with the call and yet it's coming from what? From A, or the customer can be dissatisfied whilst the call is coming from B. Please keep that in mind, because from what we're told that, like, if you look at this and this, like the customer can be dissatisfied given that it's coming from A. And also the customer can be dissatisfied given that it's coming from what? From B. So now, if you want to calculate the probability of being dissatisfied, you have to account for both calls coming from A and also coming from what? From B, isn't it? So how do you account for this? This is how you do it now. Let me remove this probability of D. So here it's going to be probability of D. It's going to be equal to. How do you calculate probability of D? Like, if it's probability of D, isn't it? They are saying you have probability of D given A, which is 0.56. And you also have the probability of what? Of A, isn't it? So in literal terms, like, it's not like I'm trying to explain this in literal terms so that you can understand where this is coming from and going. So let's assume you have, isn't it? We said it's probability of D given A. So what this means, like in mathematical terms, like I want to explain it in mathematical terms first. So what this means is you have probability of D given A, which is 0.56. Then you have probability of what's this, of A as 0.6. Now what do you want to calculate? You want to calculate the probability of, let's say probability. You want to calculate the probability of D, isn't it? On this case only. How do you go about it? D given A can actually be represented as D over A. Like I'm just explaining it in mathematical terms, please. Like it's D over A. So how do you get D now from D over A? Obviously, you can get D from D over A by saying D, by saying D over A times A. If you say D over A times A, you get what? D. And so the A's will cancel out. So in literal terms now, this is similar to what's being done here. Like we want to calculate the probability of D from this case only for now. Like we want to calculate the probability of D from this case for now. Then we also want to calculate the probability of D from this case. So how do you go about it? For the first one now, it's going to be probability of D given A times probability of what? Of A.
Sorry, what's going on?
Okay, sorry guys. This device just kicked me out. Like I don't know how, why, but I'll try to proceed from where I left off. Just to confirm, can you hear me now?
Yes, can hear you. Thank you.
Okay. And also, just to confirm, can you see my screen now?
Can see. Thank you.
Okay. So as I was saying now, probability of D given A times probability of A. This is just the same as D over A times A, which gives you what? D, isn't it? This is actually one and the same thing, just for you to actually understand. In probability terms, that's not how it is, but I'm trying to simplify it so that you guys can understand. You see? So this is for probability of defective of dissatisfied from A, isn't it? Then what about dissatisfied from B? It's gonna be probability of dissatisfied given what? B times probability of what? Of B. Then this is just the same as D over B times B. Then it also gives you what? D. So probability of dissatisfied is going to be probability of D given A times probability of A, then plus probability of D given B times probability of what? Of B. Then how do you go about? You already know these probabilities, isn't it? Then probability of D given A is 0.56 times what's the probability of A? 0.6. Then plus probability of D given B is 0.46 times probability of B 0.4. Then the answer that you get here, I think is actually the one that's written there. It's going to be 0.52. 0.52. Any questions before we go on to the second one? No, part B, I mean, because part B is a bit, it's actually everything that we've done now, but there's a twist to it that you will see. Because I feel like the moment you do part B of the question, then you'll be equipped to actually do everything. Do you have any questions? Okay, I assume everything is fine. Then, what's this? Okay. We go on to part B. What's part B saying? Part B is saying, suppose that the last customer to call yesterday was very satisfied. Then there's a full stop. Or I don't know. Very satisfied, yes. Then what is the probability? What's the probability? What is the probability that he was a caller from what? From B, isn't it? So what this means is you're actually given a condition first and foremost, isn't it? Like you are told that, okay, like the customer was very satisfied, isn't it? Okay, so solution. What are you told? Firstly, you are told that the customer was very satisfied. That's fine, isn't it? Then what is the probability that he was a caller from B? So we are looking now for the probability that like as I said earlier on, the best thing that you can do first is to write the condition. Like write the condition first, isn't it? You are given that the customer was very satisfied, which is V, as we said earlier on. Then what is the probability that he was from what? From B, isn't it? This is what you are calculating for. What is the probability that the customer was from, like the customer was very satisfied? That's one thing we're told initially. That's why there's a full stop there. Like I feel like when you do all of these questions, you see that you give you a scenario, then at the end, like there's a full stop, you see. Then you ask you the question after a certain conjunction or something. I don't know what you call those things in English, but yeah. So you're told that, okay, you're like the customer was very satisfied, that's fine, which is the condition V. Then what is the probability that he was from what? From B, isn't it? That's what you are working for. So how now do you go about this? This is how, like, it's gonna be a bit long though, but it's fine. So for this one now, according to the laws of total, what do you call this? According to the laws of conditional probability, we said probability of B given V is the same as probability of B intersection V of sorry guys, can you hear me? My Wi-Fi is really bad today, so just to confirm, can you still hear me though?
Yes, can you hear you? Thank you.
Okay. Like my Wi-Fi is really bad. I don't know what's going on, but nonetheless, I hope it's fine now. Okay, we're here. So I was saying it's gonna be probability of B intersection V over the probability of what? Intersection V over the probability of V. This is what we know, isn't it? But there are two things now that you have to know. We don't have the probability of being very satisfied. Because if you look at the data that we're given that, okay, someone can be very satisfied, isn't it? Like in this case, someone can be very satisfied, but can be from A, isn't it? Then someone can be very satisfied also, but from B. So what do you want to do? You want to isolate the being very satisfied for it to be alone, isn't it? So we can work out the probability of being very satisfied as probability of being very satisfied, but from B times probability of B times probability of being very satisfied but being from A times probability of what? Of A. It's actually what we did what? Here. Like it's just the same concept, like literally. Because for this one, as I said in mathematical terms, it's just V over B times B, then plus, sorry, it's plus, not times, plus, then plus V over A times A. Then if you do the computation, it's just gonna be V plus V, isn't it? Like, don't mind this, I'm just trying to explain how you go about such, isn't it? So it's gonna be B plus that. So what's the probability of V given B? V given B is 0.2 times probability of B, we said is 0.4, then plus what's the probability of V given A? You said is 0.11, is it? 0.11. 0.11 times probability of A is 0.6, isn't it? So in this case, it's going to be 0.2, 0.4, plus 0.11, 0.6, which is 0.416. Let me confirm my honesty. Okay. So here it's going to be 0.146. So you are done with the computation of the probability of what? Of V, which is this one. Which is what? Which is this. But now we want to calculate this one also, isn't it? Like, want to calculate the probability of B intersection V. But now the question is, like, someone would ask, like, how on earth would you calculate this, isn't it? It's actually not that difficult. So why am I saying so? Because if you come to the conditions that you are given here, like there's a link, like this is the link that you're supposed to identify. Because isn't it here we're asking, like they're asking us for probability of B given V, but we'd already said that probability of B given V is not the same as the probability of V given B. But what did we say initially when we started this? We said that the denominators are different, isn't it? But the numerators are what? Are the same. Because we say that A intersection B is the same as B intersection A. So knowing that now, we don't, like the only way that we can calculate B intersection V is if we can use either one of these two expressions. So there's no way that you can use B intersection V, so B given V, because it's actually what's being asked here, isn't it? But we can use probability of V given B. Why can we use it? Because it's actually given in our condition here. Like we already know that probability of V given B is 0.2, isn't it? So probability of V given B is given as 0.2. But how do you calculate V given B? Well, probability of V given B is calculated as probability of V intersection B over probability of what? Of B, isn't it? So if it's calculated this way now, then isn't it we had already said that this, like, isn't it we already said, like, note probability of V intersection B is the same as the probability of B intersection what? V. So this is actually what you are looking for. Like this is the numerator way. Yeah. This is the numerator that you are looking for, isn't it? Like in this scenario, I mean. Because the denominator already calculated it here. Then for the numerator now, we calculate it from what? From this expression. So it's going to be probability of V given B, which is probability of V intersection B over probability of what? Of B. Now, how do you calculate this? It's going to be probability of V intersection B. It's going to be probability of B times probability of V given B. Then probability of B, we already know it.
Sorry, you can't see what you're writing.
Sure. Yeah. Sorry. I didn't know that it stopped. Can you see now? Hello?
Oh, yes, I can see.
Okay. So now I was saying probability of V given B is the same as probability of V intersection B over probability of B. Now, if you make this the subject of the formula, V intersection B, it's going to be probability of B times V intersection, times V given B, of which we already have these expressions. What's the probability of B? It's 0.4. Then what's V given B? V given B, from this, like from the question that you have, V given B is 0.2. So it's going to be what? Times 0.2. Then for this one, 0.4 times 0.2, then you get 0.08. So now you know that probability of V intersection B, which is the same as the probability of B intersection V, is equal to 0.08. Then probability of V, we had already calculated it there. We say the probability of V is 0.146. 0.146. Now, how do you, like the question now, as it asked us, like when we modeled it here, it was saying what is the probability of B given V? So your probability of B given V is going to be equal to probability of B intersection V over probability of V. Then it's going to be 0.08 divided by 0.146, which is 0.547945 blah blah blah. Then this is how you get this answer. So just trying to see everything from the perspective that I was trying to explain to you now. Like, do you have any questions? Or let's okay. Let's just do one more. Then if you have any questions, like let's just do one more. Then if you have any questions, then we'll try to address them. Because I'm sure it might not have made sense now, but as we do a second question, everything will be fine. So similar to the question that someone just sent to me now, as they had said, it's actually the same question, but the values have just changed somehow. Because question 2 is saying 2 companies are involved in building RDP houses in the housing project in Gauteng. Then company A, as I said, please write everything as you are told. I don't like this color. Like, just write everything as you're what? This one. Write everything as you're what? As you're told, isn't it? So we know that we have what? Company A and company what? And company B. Then company A, they are saying company A built 57%. So the probability, obviously, of company A is going to be what? 0.57. Then the probability of company B is going to be 0.43. Isn't it? Then experts have determined that 16% of the houses that were built by company A have defects. Isn't it? So probability that there are defects, isn't it? Given that the houses were built by company A, it's going to be what? 0.16. Isn't it? Like, this is what that 16% is implying there. Then, and it's saying that of those houses that were built by company B is 22. So probability that these houses have defects, but having been built by what company B, it's going to be what? 0.22. But also from this now that they actually told us that, okay, the probability that these houses have defects, yet they were built by company A, is 0.16. What this will tell you is the probability that the houses do not have defects, but having been built by company A, is going to be the complement of this. So the probability of not having defects, let's assume not having defects is D complement given A. Also, please, I saw that most people make this common mistake. Like, they will say probability of D complement intersection A complement, or they will say probability of D complement of D, given A complement. Like, these two expressions are wrong, you see, because whenever you're looking for a complement, the condition does not have a complement, you see. Like, whatever condition that you be given when you're doing these probabilities, it doesn't have a complement, because the complement of A in this case is obviously B, isn't it? So there's no way that you can just come on to say no, probability of D given A complement, you see. Like, it doesn't make sense for you to do that. So what you do now is probability of D complement given A is gonna be the complement of this, which is 1 minus 0.16, which is 0.84. 0.84. Then also we come on to the B side, probability of not having defects but having been built by B is obviously 1 minus 0.22, which is 0.78 if I'm not mistaken. Then I feel like the moment you have your data as it is now, you're actually good to go. Then you go on to question A. Question A is saying, what is the probability that a randomly selected house in the housing project we have defects. So you're looking for the probability of what? Of defects, which is just the probability of D. How do you calculate probability of defects? Obviously, we know that, okay, our house can have defects, but it can either come from A, which is this, or it can have defects and also come from B, isn't it? So how do you calculate it now? As we did earlier on, it's going to be probability of defective given A times probability of A, and plus probability of defective given B times probability of what? Of B. I'll try to explain this once more using the regular approach, which is D over A times A plus D over B times B. Then you come up with D plus D. Just this, and this cancel out. Then you're done, isn't it? So, having done this, what you do is you say you already have this probability, isn't it? D given A is 0.16. Then what's probability of A? 0.57. Then plus D given B is 0.22 times what's B? 0.43. So if you do this, 0.16 times 0.57 plus 0.22 times 0.43, it's 0.1858. That's the probability for defects. Then part B now is saying, look at part B. It's saying, suppose the homeowner from the housing project is come complaining that his house has defects. So you see, there's a full stop there, meaning that this is actually the condition that you are given. So it's going to be probability of, I don't know what they will ask, given defects, isn't it? Then what is the probability that the house was constructed by company B? So we are calculating the probability of B given what? D, isn't it? So how do you calculate this? We know that probability of B given D is probability of B. Okay. It's going to be probability of B intersection D divided by probability of D, isn't it? So in this case now, if you look at the question that we did here, I want you to see something. Like, it's a trick that you normally does. Like, isn't it, for the first question, he was asking us to calculate the probability of what do you call this? Of being dissatisfied. Okay. In this case, he was asking us to calculate the probability of being dissatisfied. Then we got 0.52. But now when we did our computation here, it was actually like the numerator was probability of V, which is very satisfied. So we had to do a similar calculation to the one that we did here. But now, in this case, now we are more concerned about what? About being very satisfied. We can see that the probability of D, which is the denominator, is actually what we've calculated above in the first question. So what he does is you set his questions in such a sequential order where the first one that you compute here, you have to use it maybe on part B as we are doing now, or there's a way that he will actually not ask you to use that very same answer like how we did in the first one, in the first example. So please watch out for that. So for this one now, is probability of B intersection D over probability of D. We already know that probability of D is equal to what? 0.1858. We already know the denominator right now. You see? Then we want to calculate the numerator now. How do you calculate the numerator? The numerator is saying probability of B intersection D, isn't it? But probability of D intersection B intersection D is the same as the probability of D intersection B. Keep this in mind. Then, how do you calculate this? We go on to the data that you are given. What do we have? do we have something that's linking a condition that's linking B and D? When you come here, we can see that, yes, we do. We actually have this one, which is the probability of D given B, which is given as 0. What did they say? It's given as 0.22. So how do you calculate this one now? It means that, okay, probability of D given B is equal to 0.22. But how do you get this? This probability of D given B is the same as the probability of D intersection B over probability of B. You see? Then what's our main point of interest? What you are interested in is this numerator, which is here, and which is also the numerator here in the computation that you are trying to achieve. Then probability of D given B times probability of B is the same as the probability of D intersection B. Then 22. And what's the probability of B? Probability of B is 0.43. So it's going to be times 0.43. So 0.22 times 0.43, you will get 0.0946. See, then having this now, you can come onto your computation that you did here, like how now our main interest is probability of D of B given D, which is said is going to be probability of B intersection D over probability of D. Then what's B intersection D? We said B intersection D is 0.0946. Then what's probability of D? It's actually what we've calculated here, which is 0.1858 divided by 0.1858. Then your answer will be 0.509149496 blah blah blah. Then that's how you do it. So as you can see, these two questions are the same. Like they're literally the same. Like this is like, well, everything that we've been doing here is actually base theory. Like this is base theory and law of total probability also. Like I don't have to take you through the formulas because they are a bit long and you might not actually understand. But if you do questions as we did now, I feel like it makes more sense and it's a bit clearer. So yeah, do you have any questions? Any questions? Any questions? Okay, so it's fine because let's do question 3. You see, because I don't know. Firstly, when I compiled these questions, honestly speaking, I didn't know that you guys had a quiz. But if you are in the WhatsApp states group, someone just posted a question now, then said, "I kindly help." The question that they posted is actually similar to question 3 in this document that I just gave to you now. Like it's actually similar. Though now it's saying a machine is tuned correctly 95%, but in his or a question, it's saying it's tuned 92%, isn't it? But let's just do question 3. Then I feel like from here I'll be able to address any questions that you guys might have, because it's actually one and the same thing. Like everything else, the moment you know how to tackle such questions, everything else is just the same. Like it doesn't change. The format won't change. So question 3 is saying a machine is tuned correctly 95% of the times. Yeah. So you see, as I told you initially, he just told you that it's tuned correctly 95% of the time, isn't it? But we know that probability is supposed to add up to 100. So where's the other 5%? You're supposed to figure that out on your own, isn't it? So now when this question is saying a machine is tuned correctly, so probability of being correctly tuned, I have a problem with writing this as they are now because I won't be able to see. Okay, so it's probability of C is equal to what? 0.95, which is being correctly tuned, isn't it? But now, what's the probability of being wrongly tuned, isn't it? Which is the complement of this. The probability of being wrongly tuned, which is C prime, C complement, is actually the complement of this, which is 0.05. You see? Then it goes on to say if the machine is correctly tuned. So you already know that, okay, the condition is if it's correctly tuned, which is C, isn't it? It produces defective items 3% of the time. So probability of it producing defective items having been correctly tuned is 0. What? Sorry, it's 0.03. It's 0.03. Then, if not, the probability of producing defective items 0.75. So this if not is actually implying that, okay, if the machine is correctly tuned, isn't it? It produces defective items 3%. But if not, this if not is implying that if this machine is not correctly tuned, isn't it? Then it produces defective items at 0.75. So what this means is probability that if it is not correctly tuned, which is the condition, the probability that it produces defective items is definitely going to be 0.75. But now we know that given these two conditions, whatever probabilities that will come up that include these two conditions should add up to 1, isn't it? So as I said earlier on, there's no complement of a condition, but something that comes prior to the condition is the one that is a complement. So in this sense, it's going to be probability of D complement, isn't it? D complement in this case, obviously, it's going to mean that your items are not defective. Given C, it's going to be the complement of this, which is 1 minus 0.03, which is 0.97. Then probability of D complement given C complement, it's going to be 0.75, which is 0.25. So again, the moment you have this, you're good to go. The question is saying, what is the probability that a randomly selected item from that consignment, from a consignment item produced on a machine is defective? So if something is defective, solution, we said if it's defective, it can be defective from C or defective from C complement. So probability that it is defective, isn't it? It's definitely going to be probability of D given C times probability of C plus probability of D given C prime times probability of C prime. As I said earlier on, I'm just going to keep on doing this just for you to see. D over C times C is the same as D. Then plus D over C complement times C complement is the same as D. It's like that's how you go about it, isn't it? So now it's going to be equal to, what's probability of C? Probability of C is 0.95. Then probability of D given C, sorry, is 0.03. Then plus, what's probability of C complement? 0.05 times, what's the probability of D given C complement? 0.75. Then this becomes 0.95 times 0.03 plus 0.75. Then you get 0.066. Is the answer given there. Then part B, like you can see that all these questions follow one single trend. Like it won't change. The moment you get a hold of this, like if you just do these 3 examples that we did now, you actually get through, like you actually be able to navigate your way through this, because it's just one and the same thing. It doesn't change at all. Then part B is saying the first product of a test run was inspected and found to be defective, you see. So it's found to be defective. So if it's found to be, then you know that, okay, this is our condition. So our condition is what? It's found to be defective. That's fine. Then what exactly are they asking of us to do? What is the probability that the machine had been correctly tuned? So we want the probability that it's correctly tuned, given that it comes from what? Sorry, the probability that it's correctly tuned, given that it was found to be what? Defective initially. So it's going to be probability of C intersection D over probability of what? Of D. You see? Then probability of D, we already have it because that's what you calculated there. Probability of D, it's going to be 0.066. Before I proceed, let me address another issue also. If the question had said, the product was inspected and found to be not defective, isn't it? If they had said it's not defective, then our model was going to be probability of C given D complement, isn't it? Which is probability of C intersection D complement over probability of D complement. So you can see that in this case we calculated for defective. So we have to calculate for what? For defective complement using the first method that we did initially. So defective complement can be calculated as, because we know that defective complement can either come from here or can come from there. So it can be probability of defective complement given C times probability of C plus probability of defective complement intersection C complement times probability of C complement. Like it's actually the same thing, but you just have to keep note of what exactly will be required of you to compute on the denominator. I hope it makes sense. So probability of D, we already have it as 0.066. That's fine. Then for the numerator now, okay, they want us to calculate probability of C intersection D, but what we know is this is equal to D intersection C. That's fine. Then what do we have? Like the link between D and C. We know that, okay, we have this condition that you're given here. Probability of D given C is 0.03. But how do you calculate this? Probability of D given C is equal to probability of D intersection C over probability of C. Then probability of D intersection C is going to be probability of C times probability of D given C. What's the probability of C? We say it is 0.95. Then probability of D given C, we said it's 0.03. So it's going to be 0.03 times 0.95, that's 10. It's going to be 0.0285. Then the moment you have this, you know that this is your numerator. This is your numerator. Then your denominator, you already have it as here, denom. So how do you calculate what you are required to calculate, which is probability of C given D? C given D, it's going to be your numerator, 0.0285, divided by your denominator. Where's the denominator? 0.066, 0.066. So it's this divided by 0.066, which is 0.431818 recurring. And you express it in however form that you want, like number of decimal places that will be required of you to do. Any questions? Like before I ask for any question, does it make sense though? Is it clear?
Yeah, it does. Thank you. May I ask a question?
Okay.
I want to ask, how do we get the sample space for questions like maybe Tumi has 13 different pamphlets which he wishes to put randomly in 4 mailboxes? So how do we get a sample space for that?
Isn't it, as I had said earlier on, it's either 4 to the power 13 or 13 factorial. then calculate and see which one will give you like a reasonable probability, then that will be it. Because okay, actually before we do that gambling thing, isn't it saying 13 different which he wishes to, no, it's actually 4 to the power 13, I think. Because isn't it you have 4 boxes, which is A, B, C, and D. I'm really not sure about this though, because I'm trying to see. So in how many ways can you actually do this? Because A, like we have 4, isn't it? And they can actually receive how many, isn't it, you said he has 13 items. So if he has 13 items, then obviously this is going to be 13. Let's assume that he gets 13 here, then 13, 13. Wait, is it 13 to the power 4 or 4 to the power 13? Just confirm on these 3. Like, I'm really not sure, honestly. But just try amongst those 3. That's where your sample space will be. Because I didn't do the sharing sample space deep enough to be able to answer. Like, I'm really sorry about that. But yeah, just try amongst these 3. You will definitely get your sample space somewhere there. Is it fine? Because I feel like 13 to the power 4 is more. See? Yeah, 4 to the power 13, I feel like it's. I mean, 13 to the power 4 might be a bit smaller. So I feel like this is not there at all. So try between those 2. Is it clear?
Yes, sir. Thank you.
Sharp. Any more questions? Okay. I assume you don't have questions. So yeah, guys, thank you so much. I feel like this is the end of this session for probability based what. And one thing that I can guarantee is you are never gonna see counting methods again in your life. Only in the test, in the exam, I mean. Like you just bring maybe 2 or 3 counting methods. But even if you didn't understand them, or even if you would have forgotten by then, it's still fine. You can as well do without them, because everything that you're gonna do now from lecture series 5, like it might seem as if it's a bit complex, sophisticated, but it's really not, honestly. Like, trust me on that. If you feel like there's a need for sessions or for another session or something, you just tell me, then I'll post in the group. Then we'll do the session as per the lecture series that you will be doing. And one more thing, please don't panic about tomorrow's thing. It won't be as difficult as you guys might think. Like it's actually everything that you have done now, and some of the questions you might see that is actually repeating more or less. So best wishes for tomorrow's thing. And if you have questions, I'm really sorry I won't be able to attend to them now, because as soon as I'm done with this session, there's another one that I'm supposed to be having. Well, I'm the one now who's a student also, you see, because there's a part that I don't understand pertaining to what I'm doing now. So I won't be able to answer them. Maybe I can only do so tomorrow in the morning, but I know that you guys won't be able to, because you're writing also in the morning. So again, best wishes. If I'm able to come for the invigilation, I'm not sure, I'm here to confirm. I will see you there. But if not, then best wishes in tomorrow's thing. Like, don't worry at all. It won't be difficult at all. As long as everything is fine, just know that you definitely make it. I don't know if you have any questions, any suggestions, or what. Okay, so if there are no questions, then thank you so much. We'll see each other in the next session, or in the next tutorial, or whatsoever. So yeah, thank you so much, guys. Again, best wishes. We'll see you tomorrow. Oh, and also please, can you just ensure that everyone leaves the meeting, because that's the only way that it can only be able to save fast enough, so that you can be able to access the recording if you want to use it. So please just make sure all of us leave the meeting, then it can record. So sorry, it can save the recording. Thank you. Can the three guys who are still in the meeting please exit? Please, please, please. Hallelujah.